think that's good. Okay. Let me start this. Hi everyone. I'm going to talk today about my work on investigating disparities in air pollution exposure in Canada from the local to the national scale. So the first poll question to kick us off is, what is your level of knowledge about environmental justice? Okay, cool. I will stop sharing the poll. And it looks like there are a few people who are quite well aware of this. Most people are generally aware, have heard of it, and a few people have never heard of it. So I'm just going to quickly go over some foundational. Okay, there we go. Sorry. Quickly go over a little bit about environmental justice. It's generally defined as having three aspects of justice: recognitional, procedural, and distributive. Recognitional being just recognizing disparities in fundamental human rights. Procedural justice being more around who's involved in decision making for any process that affects environmental quality. And then distributive is mainly around how environmental harms and benefits are distributed among different groups in a population. And so my work that I'm presenting here will focus on mainly procedural and distributive aspects of justice, but all three are really important, and this is just one small part of trying to get at environmental justice in Canada. Okay, so on June 13th last year, Canada recognized the right to a healthy, clean, and sustainable environment for all Canadians. On that date, the Strengthening Environmental Protection for a Healthier Canada Act became law. But what does that actually mean? The government didn't really know either. They have given themselves 2 years to figure out how this right will be implemented. And so this presentation and my work is in a vein kind of trying to help address one aspect of a healthy environment for Canadians. Just one small part of that, which is assessing and improving disparities in air pollution exposure. The motivating questions behind my whole thesis, my whole work, are number one, does air pollution in Canada disproportionately affect vulnerable groups? And if so, what technology and policy interventions could reduce these disproportionate impacts? And number two, how can air quality modeling tools be adapted to be fit to purpose given different pollutant chemistries, spatiotemporal scales of interest, and computational resources for environmental justice analysis? And I'm beginning with the national scale analysis. As I said, this goes from the national to the local scale, but why is a national scale analysis important? And assessing disparities on a national scale is really necessary for many reasons, including having a common basis for comparison, evaluating national policies, or making recommendations to the federal government, like what I just mentioned, and also comparing different regions and prioritizing future action. And a lot of what I'm focusing on at the national scale is Canadian industry and the disparities in air pollution burdens. The main reasons for this are, number one, the magnitude of the burden. Living near industrial facilities can be detrimental in a wide variety of ways, from pollution, discharge to air and water, noise, odors, traffic, decreased home values. There's really a lot of effects of living near industrial facilities. And then number two, the source characteristics of industry related to air pollution. It's one of the few air pollution sources that is relatively stationary, relatively consistent. Other really big emitting sectors like traffic are pretty diffuse, a lot harder to control. And then wildfires are also a big contributor to air pollution in Canada, but they're less predictable, less controllable. And then finally, the regulatory potential of Canadian industry, because the government actually has good authority to issue permits and enforce infractions. And there are three main parts to the assessment that I'll be talking about in this presentation. Number one is to determine the extent of disproportionality in emissions. Number two, to assess the siting practices near potentially vulnerable groups. And then number three, to calculate population-weighted exposure to PM2.5 disaggregated by group. Okay, so that brings us to our next poll question. What do you mainly think of when you hear the phrase potentially vulnerable group? And you can pick more than one. Okay. It looks like there's a really good distribution between different groups. And so I'm going to stop sharing this poll. Exit out of it. Okay, so yeah, all of these groups are ones that may be more vulnerable to air pollution exposure, as well as potentially vulnerable in general. And we traditionally think of the elderly and children as more physically vulnerable to air pollution, but social determinants of health, like social inclusion, employment, and education can also make other people in these other groups more physically vulnerable to air pollution as well. And so I may, just as a note, I may use the phrase potentially vulnerable group or vulnerable group interchangeably, just because it's potentially vulnerable group is kind of a mouthful, and I'm looking at many different groups in Canada and how environmental burdens are distributed. I'd also like to note that I'm focusing my work on the first four groups here, just due to past research into environmental justice in both the US and Canada. And then I'd also like to note that I'm including white populations in a lot of my analysis. You'll see them come up as a comparison group, both just to, as a good comparison to some of the other racial and ethnic categories, and also in recognition of the intersectionality of environmental justice. You know, that there can also be recent immigrants, low income people within white populations as well. And another note, I'd like to say that I'm focusing on PM2.5 and PM2.5 precursors. PM2.5 being what's directly emitted as PM2.5 from industry, with the requisite picture of PM2.5 compared to human hair, particulate less than 2.5 microns in diameter. And then secondary PM2.5 is also really important for industrial emissions because industries emit a lot of these precursors like nitrogen oxide, sulfur dioxide, volatile organic compounds, and ammonia. And I'm focusing on PM2.5 just because of the well-documented health effects of PM2.5 exposure, but this is not to say that there aren't many other industrial pollutants that are really important for air pollution. However, the health effects of these other pollutants are, and also mixtures of these other pollutants are less well characterized. And then modeling these other pollutants, the chemistry and the transport is more complex. So since this hasn't, this type of analysis hasn't been done before in Canada, we're looking at PM2.5 first, but I think that that is a very important direction for future research. And so the first question in our analysis is simply about the nature of Canadian industrial emissions. We want to know how emissions were distributed before we begin any further analysis. And we know that there's documented disproportionality in many emissions categories for both air pollution and greenhouse gases, even among sources with similar characteristics. And past research, mainly from Mary Collins in the US, has shown that industrial emissions are industrial emissions there are unequally distributed among industrial subsectors and among facilities. We believe that Canadian emissions may be similar, but this pattern actually hasn't been demonstrated here before. And to do this, we're using data from the National Pollutant Release Inventory, which is a self-reported database of industrial emissions in Canada. And our methods, we're looking at all industrial subsectors. That's kind of the level that you generally know, like utilities, oil and gas extraction. It's pretty familiar to a lot of people. And we calculated 3 different criteria to look at these industrial subsectors and the disproportionality. And so the first being emissions, just is this a high emitting subsector? Emissions per facility, are there a lot of emissions per the number of facilities within the subsector? And then emissions per GDP. And so through an additive ranking system of all those criteria, we selected 9 subsectors for further analysis, just to kind of concentrate our assessment on the most important subsectors. And to look at disproportionality within these subsectors, we calculated the Gini coefficient and then the portion of high emitters, or portion of emissions that high emitters represent. I do also want to say that there are a lot of questions around the MPRI of whether it's accurate or complete. Accurate because it is a self-reported database, and complete because there are, I would say, some like more normal exemptions for size of company, number of employees, things like that. But then there are also some exemptions that are a little bit weirder around fracking and oil and gas exploration. So that is to say that if we don't find that a subsector is disproportionately affecting a certain group, that's not to say that there isn't a potential leak there. We might just not have the data to actually say that it's there. Okay. And so this results in 9 subsectors that we're assessing. Like I said, I'm not going to go over these too much, but when we look at disproportionality within these subsectors, we do see, oh yeah, okay, you can see my cursor, great. We do see that high emitters within each subsector consistently represent less than 25% of the facilities within that subsector, and then also consistently represent over 50% of the emissions. So that indicates a good level of disproportionality. And then also Gini coefficients, how we calculated those, it's basically the ratio between these 2 areas under the perfect equality line and then the actual line of what you get when you plot cumulative percentage of facilities and cumulative percent of emissions. So a Gini coefficient of 1 means perfect inequality, and a Gini coefficient of 0 means perfect equality. And as you can see, these Gini coefficients are quite high, quite close to 1, indicating that there is a lot of disproportionality for emissions of each of these pollutants within each subsector. Next, we want to know, does industrial siting disproportionately affect vulnerable groups? And this is because the roots of the environmental justice movement in the US was actually, it started with the proposed siting of a hazardous waste landfill near a predominantly Black community in Georgia. And a large body of research in the US has shown that industrial facilities are often disproportionately located near vulnerable communities. However, we don't have past research on this topic in Canada as a whole, but we do have reason to believe that this is true with much of the environmental justice work surrounding industrial facilities taking place in Sarnia. And to do this, we also need data on population, which we get from the 2016 Canadian census at the dissemination area level. We look at categories related to race and ethnicity, income, and immigration status. And then we also use information from the population of Canada on urban and rural populations to divide our assessment into urban and rural sections because Canada is a big country, a lot of it's rural, and we expect to see different results. And so when we relate, we're relating siting with population patterns by doing a buffer analysis, which is basically drawing a buffer of 1.5 kilometers around each industrial facility, and then we calculate the comparative environmental risk index to link disproportionate siting with each demographic group that we're looking at. And the index, or SERI, as I will refer to it, is basically a ratio between the number of certain group exposed versus the number of the total population exposed. So a SERI value greater than 1 indicates that that group is disproportionately affected, and less than or equal to 1 is that it's not disproportionately affected. And so results of this are that we do see disproportionate siting practices affect vulnerable groups across subsectors. I have a table here. Apologies, it's a bit hard to see what exactly is written, but basically the yellow bars, or the yellow boxes, indicate that there is a disproportionate siting link between that subsector and that group. And then for future analysis, we'll get more into this, but red vertical lines indicate that there is a disproportionate siting link for high emitters, and then crosshatch is that there's disproportionate siting for both all emitters and high emitters. And so we can see that all potentially vulnerable groups have a disproportionate siting link from at least a few subsectors. And then we want to know, are the highest emitting facilities disproportionately sited near vulnerable communities? Because this is kind of getting at that area of double disproportionality, as we call it, which is this disproportionality that we're seeing in emissions, and then the social inequity that we're seeing on the demographic side, and how those patterns are overlapping to actually create this double disproportionality of the highest emitters affecting the most vulnerable people. And so we see that some vulnerable groups are affected by living in proximity to high emitters. You can see the red squares and the crosshatch squares indicate that there is a disproportionate siting link there for high emitters. Generally, it goes down when looking at high emitters versus all emitters, just the number of disproportionate siting links. But there are notable exceptions to this, which are urban indigenous populations and then urban white populations, where they actually have new disproportionate siting findings for high emitters compared to all emitters. And then in rural areas, we also see similar patterns of this going down, but we do see an exception for rural white populations. And then another way to kind of get at how industry is affecting people, we wanted to look at who's most affected by living near clusters of facilities. To do this, we calculated what we're calling an MPRI influence score, basically to determine the number of people living within overlapping buffers from multiple facilities. So as an example, here, if you lived in this area of overlapping buffers, your MPRI influence score would be 3. And clusters do show different proximity patterns. Almost 90% of Canadians just don't live within 1.5 kilometers of an industrial facility, which is good. But some communities have members who live within 1.5 kilometers of up to 8 industrial facilities. And we find that low-income, Black, and visible minorities not included elsewhere, which is a census category, are the groups most likely to reside in proximity to multiple emitting facilities. And then now we're getting into like a little bit more of the actual PM2.5 exposure side, because while siting is important, we also want to look at who's actually exposed to PM2.5 from industry. And so as a first pass, we were asking, do industrial emissions actually contribute significantly to PM2.5 exposure? And the answer is quite a bit in some areas. This is, apologies if you can't see the screen, but this is, the red is basically 100% of total PM2.5 concentrations coming from NPRI emissions. And so you can see in some areas there are quite high proportions of the total PM2.5 concentration coming from industrial emissions. And next we want to look at how do industrial emissions contribute to the PM2.5 exposure of vulnerable groups. And this is because marginalized people are often exposed to disproportionate amounts of PM2.5 in Canada, and disparities in PM2.5 exposure contribute to health disparities even in areas with relatively low levels of PM2.5. Previous research has shown that without targeting equity specifically, it's often not a co-benefit of environmental regulations. And so we've also seen this in Canada, where PM2.5 emissions have generally improved over time, while disparities generally have not. And to do this, we need a model. So the model that I'm going to be using is called Global INMAP, which is a reduced complexity air quality model that focuses on PM 2.5. And it's a really good one for looking at these questions of national scale exposure, but you want to distinguish between different populations because it has a variable grid, so we can get big grid cells, have it run efficiently in areas where there's no population, and then have smaller grid cells and be able to distinguish exposures in urban areas. And for this, we'll also need more data. We're still using the 2019 NPRI emissions, but assuming information that's not included in the database, like stack height, stack diameter, exit velocity, and exit temperature. And then we also need a few other model inputs, which are published data from INMAP Global, because it takes the output of a full chemical transport model to get parameters like meteorology and some different chemistry parameters. And the results of this are that we see the most exposed urban group for all subsectors is Indigenous, while rural patterns are a little bit more complex. So this is a heat map. It's a little bit hard to read here again, but this is basically showing the difference by population from the total population weighted concentration in micrograms per meter cubed. And demographic group is down here, and then we have individual subsectors, or looking at all subsectors on the top. So a blue square indicates that they're less exposed, and the darker blue is they're even less, like the darker the blue, the less exposed relative to total population, and the darker the red, the more exposed relative to total population. And so here, this little square, if you can see, is the Indigenous exposure to all emissions from all subsectors relative to the total population, and that's the highest in urban areas. And then in rural areas, we do see quite a few higher exposures relative to the total population for different racial and ethnic categories. But interpreting patterns in rural areas is a little bit harder because the model doesn't do quite as well in rural areas. The uncertainty is a little bit higher. And then also because population settlement patterns are pretty different. Like West Asians in rural areas have the highest exposure relative to total population that you can see here, but they actually have only about like 2,000 people living in rural areas in Canada. So it's still important to see where those 2,000 people are living relative to other people, but it makes it a little bit harder to get at a generalizable pattern. And it's easy to see that the white population, which is here and it doesn't really show up, it's pretty much on point with the total population exposure, and that's just because there's a lot more white people in urban areas, or in rural areas, excuse me. And so from this, we wanted to know how PM 2.5 exposure is affected by the highest emitting facilities. And to do this, we ran two illustrative scenarios, one being no high emitters, which is just basically removing the high emitting facilities from the data set and seeing how exposures change. And so I want to note scale in all three of these. It looks like we're increasing stuff here, but the scale is quite different for all of these plots. And then the second scenario that we looked at was average emissions, and so this is not changing the total amount of emissions within a subsector. It's just spreading them out evenly throughout industrial facilities and seeing how that changes population exposure. And what we find from this is that high emitters cause most of the industrial PM 2.5 exposure for the total population and also for many vulnerable groups. This is another heat map showing the difference between the base case or the actual emissions in our kind of thought experiment scenario that we were running for average emissions. We expect, just due to the disproportionality in emissions within subsectors, for exposure to go up generally for everybody. And then we expect exposure to go up the least for groups who are already exposed to the highest emitting facilities in the subsector. So as you can see, urban Indigenous populations right here, with the circle size being the size of the absolute change and the color being the size of the percent change, that they are actually the most exposed to high emitters. And with this average emission scenarios, urban total population rated exposure to PM2.5 increases by over 4 micrograms per meter cubed, or by about 750%. So that's just showing how disproportionately spread out the emissions are to begin with. And both scenarios point to high emitters most affecting urban indigenous populations. The conclusions from this national scale analysis of Canadian industry are that our results support the existence of double disproportionalities, where the highest emitting facilities also disproportionately affect some vulnerable groups. And then also, we hope that these results identify potential areas for policy intervention to both effectively and efficiently reduce disparities in exposure to environmental hazards. This being done through changes in community consultation processes, through more stringent permitting requirements, continuous emissions monitoring, or stricter enforcement of existing regulations. And then, as promised, I'm going from the national to the local level. I really like the hyperlocal, with this looking at a project in Strathcona in Vancouver. And the motivation for going local, because I just said the national scale analyses are really important, is because local scale analyses are also really important. And looking at disparities at a local scale, people are starting to pay more attention to community scale air quality, and not just whether our air pollution in general is, Clean Air Act compliant or federal government standards compliant. And one example of the codifying of this in the US is Justice 40. We also see the proliferation of low-cost and mobile sensors, allowing more communities to have fine-scale air quality measurements. And this is really good because air quality varies at a fine temporal and spatial scale. And differences can also be really important for environmental justice concerns. But how do we actually contextualize all of this local air pollution data and add value to local scale analyses? And we believe that one way this could be done is that we think residents are experts in their own environment, and that citizen engagement can improve, outcomes. Okay, third poll question. How familiar are you with the Strathcona neighborhood in Vancouver? Okay, so it looks like some people are very familiar. We have a pretty good spread there, but more people say not at all. Okay, so I'm going to go a little bit into what the neighborhood is like. This is an aerial view of Strathcona. It is just east of downtown Vancouver. It's a neighborhood with a strong sense of community, a lot of cultural richness, a lot of important community spaces. But it's also a neighborhood that has the highest low income rate in Vancouver, the largest Indigenous population, and also has a high proportion of seniors and then other people with health vulnerabilities. It also is close to or contains a lot of air pollution sources. As you can see, the port is right there. It's just on the north edge of Strathcona. However, this strong sense of community also leads to a strong residents association. And so in partnership with the Strathcona Residents Association, we actually implemented a monitoring network for air quality in the neighborhood. We put up 11 low-cost sensors that measured PM2.5, NO, NO2, ozone, and carbon monoxide. And you can see over here, this is what these low-cost sensors look like. You just attach them to a fence or something with fairly good airflow. And then these green dots on the map are where our sensors were put up across the neighborhood. We tried to get a good spread. And we think that it is a fairly dense monitoring network for such a small area. But to kind of get at this question of how community members can add value to local scale air quality monitoring, we conducted a community mapping event where we actually printed out maps of Strathcona, had attendees mark on the map what they thought were important air pollution sources that only locals might know about. And then they also could describe on a sticky note more about those sources. So some air pollution sources that came up pretty frequently were construction, places where cars were frequently idling, where they knew like their neighbors had wood stoves maybe. And so this was overall a pretty good gathering of getting community data that wouldn't show up in a publicly available data set. And then last poll question. How familiar are you with air quality assessment techniques like land use regression and baseline concentration separation? Okay, so it looks like most people are somewhat, next not at all, and then we have one very, okay, awesome. Okay, so I'm just gonna quickly go over what these techniques are. And so starting with land use regression, essentially it's just taking in a bunch of different land use variables and creating a statistical model of air pollution. And baseline separation is just recognizing the fact that air pollution concentrations are made up of multiple signals. Maybe there's a regional background, a citywide background, and then you have all these local peaks in air pollution from maybe more local sources. And if you're looking really local, like even like tailpipe emissions can be a peak. But this is important for us because we want to mainly look at the peaks and not so much what the city and regional background. So we're trying to separate those out. And as kind of a pilot study of how to incorporate community data into air quality modeling, we used it in a land use regression. We used data from our community mapping event, which marked the more stationary air pollution sources, and then we also use information from a survey that the Strathcona Residents Association conducted before we even started our project. And this mainly has like streets of concern, areas where they're concerned around like bus stops or the railroad, intersections. And so we took all that information and we start with a lot of land use variables for both the traditional, what we're calling a traditional LUR, and then a community LUR. And then from those land use variables, you want to select what are the most statistically significant ones for what you're trying to model. So in our traditional LUR, we find our very standard land uses. We have like transit, population, data that's statistically significant for predicting air pollution. And then for our community LUR, going through the same variable selection process, we see that these community variables actually do supplant the traditional variables for all three of the pollutants that we're looking at, which are NO2, NOx, and PM2.5. And so these variables that made it in are mainly around streets of concern or the ratio of the streets of concern to all streets, and then also distance to an intersection of concern. And we find that including community data may help local modeling. We're not saying that this is a shining example of how you should do a land use regression, because we don't have too many monitors and it's quite a small spatial area, but we do see improvement in model adjusted R squared when we're looking at the community LUR versus the traditional LUR. And then we also see improvement in the range of leave one out cross validation, R squared as well. And so these are just maps of the traditional LUR for Knox and community LUR for Knox. I apologize that I don't know if I can make the bottom bar go away, but if not, then it's fine because there's not too much there. Just that the scale goes down to 0, and you can see that the concentrations generally level out a little bit in the community LUR, where we have, like, for example, the lowest concentration here. And this concentration is still quite low, but does increase a little bit. And then our second analysis, I think it's fine, sorry. I don't want to. Our second analysis is around aligning the peaks that we see after doing this baseline separation in NO2 Knox and PM2.5 with our community reported events. And so we're taking data from the community mapping, which is more of the transient air pollution source data that people marked, and that was just fires in the community. And then we also take data from Smell Vancouver, which is a citizen odor reporting system created by researchers at UBC. And so this is just kind of an example of what baseline separation looks like for our data. We're trying to get the highest peaks that might be noticeable to somebody for them to report it. And I apologize that this is still not super clear, but basically this is a time series of PM2.5 for one monitor. And we see this blue line is the low-cost sensor data. After that's been calibrated, that's reported at every 15 minutes. And so we take the baseline as a moving average and create this red line of our baseline, and then define peaks as a multiple of the baseline concentration. And so you can see these dots here are identifying what we're calling peaks. And so what we see when we're looking at peaks, Small Vancouver air quality events don't necessarily capture the highest peaks. This is basically another sort of time series with each marker being, the color being the monitor, and then the shape being the pollutant. And then these vertical blue lines are the dates that we have odor reports for Small Vancouver. And so basically just trying to see if these peaks align with the vertical lines that we have. And you can, even if you can't see it super well, you can kind of see that it generally doesn't have, there isn't a lot of alignment between these peaks that we're plotting and these vertical lines. And we think that that may be because Small Vancouver reports are generally reporting things that people, like I said, can smell, like volatile organic compounds, and that might not be associated with peaks in our data for PM2.5 and NOx. However, we do see that community reported air quality events, which were fires, do capture some of the peaks. You can see right here, a lot of these peaks align with this red vertical line, which is a reported fire. And that is actually a canister fire that happened in the neighborhood. And then we do see a high value in one monitor for PM2.5 right here. And that's the fire at Valley Village that burned down. So you can see some of these do show up in our monitoring data. And our results generally for the Strathcona study suggest that community knowledge can be valuable beyond just increasing engagement, and that community source data on their most concerning pollution sources and odors can be helpful for mapping and interpreting data from local air quality monitoring networks. The overall key contributions of my work, I'm hoping, are to advance understanding of the nature of air pollution and environmental justice in Canada, to identify important drivers of disparities, and suggest practical solutions for mitigation, and then also to contribute to the available methods for researchers, practitioners, and activists studying environmental justice in Canada. I have a few future directions that I want to note. There is ongoing research in Amanda's group on industrial pollution enforcement actions and population exposure. I believe that we need to continue to perform national scale analyses for environmental justice and air pollution. And I'd also really like to see more work on cumulative effects of air pollution and more policy-related intervention scenario exploration, as well as, really importantly, more publicly accessible data surrounding air pollution. Thank you for paying attention, and thanks to funders and mentors and collaborators.